thanks again for the introduction, and hello from my side, and welcome to the presentation. Yeah, my name is Erik Stehle. I'm from the University of Stuttgart, where I'm a PhD candidate, and I will talk today a little bit about fastening of a gusset plate to concrete, or to be a little bit more specific, to a concrete corner by means of post-installed anchors and the numerical investigations I performed for this topic. So first of all, I will give a little motivation and problem statement, and I will then turn to the numerical investigations itself and the numerical results. In the end, I will talk a little bit about an analytical design approach which uses the methods provided by the Eurocode for such anchor configurations. And yeah, in the end, it gives a little summary and conclusion. So what you can see here is the global seismic hazard map and some of the major earthquakes that happened in the past decades. And it becomes apparent that earthquakes are still one of the most devastating natural disasters today, as we can see from the high number of casualties and also from the high economic losses. And this high level of devastation is also a result of the collapse of many buildings due to the seismic actions. And thereby, I'm not only talking about older masonry structures, but also a large number of reinforced concrete structures are collapsing during seismic events. And these structures are mainly reinforced concrete structures which were designed before the introduction of modern seismic codes. So basically, they were not really designed to withstand the high demands that are imposed on a structure during such a seismic event. And these reinforced concrete structures, they are particularly prone to unfavorable brittle failure modes, such as, for example, beam column joint failure or column shear failure, or soft story mechanisms. And therefore, such buildings need to be retrofitted so they can improve their performance during future earthquakes. And one popular way to strengthen such existing structures is the addition of steel bracings. And generally reinforced concrete structures, such as, for example, reinforced concrete frames, as we can see in the picture, they work very well under gravity loads. However, in case of seismic demands, the performance of those buildings is, or maybe rather, insufficient. So a strengthening of the structure with steel bracings results in an alteration of the load transfer mechanism from a moment resisting frame to a truss mechanism. And since the actual capacity and stiffness of reinforced concrete members is higher than their flexural capacity and stiffness, the alteration of the load transfer mechanism results in a global increase of the strength, stiffness, and depending on the steel bracing, also an increase in the ductility of the complete structure. The principles of all these strengthening solutions with steel bracing is actually well known, but the question is what is a good solution to connect these additional structural elements to the existing structure? And here, direct connection between the steel bracing and the reinforced concrete frame has several beneficial characteristics, such as the practicability, a low invasiveness of the solution, and also a high adaptability to the structural preconditions. So therefore, today I want to discuss such a direct fastening solution, where we use post-installed anchors to form such a connection. And I also want to discuss some of the challenges which arise when we want to design such a connection with post-installed anchors. So generally, when we use post-installed anchors, often the concrete-related failure modes, such as concrete cone failure, are governing the design. They're also often the most critical failure modes because they have a rather brittle failure. And this is especially the case here, where we have only a limited area or volume of the concrete where the concrete cone or the breakout body can form because of the narrow reinforced concrete members, so the beams and the columns. When we look at the connection here, we can basically describe it as two anchor groups which are located perpendicular to each other. And these two anchor groups basically share a breakout body. So we have each of these groups has a breakout body, and basically those are overlapping. In addition, we have a potential mutual effect of these two perpendicular anchor groups, which might be positive or negative, which we actually don't know. And also for the engineer in the practice, there are no design provisions in any codes or standards provided for these kinds of connections. So therefore, the numerical investigation that I performed here in this study basically serves two purposes. So obviously the first purpose is to get a better understanding of this breakout behavior of such a corner configuration. But also the second purpose was to do some preliminary analysis on such connections for the experimental work that followed them. What we can see here is the dimensions and the discretization of the investigated specimen. And as you can see, the concrete specimen is not modeled as a beam column joint per se. So this was done to exclude additional effects such as the inward bending of the reinforced concrete members when the steel bracing would be in tension, or the frame action effect on the gusset plate, which also results from the inward bending of the concrete members. Furthermore, there was no reinforcement considered in the specimen. So basically, this approach really allows us to put the focus on the geometrical influences of such a corner configuration. Of course, then in a second later step, we can also investigate on the other effects as well. But in my opinion, it doesn't really make sense to do it all in one term, but just it was better to do it step by step. The concrete elements in the simulation were discretized with 4-node tetrahedral elements, as we can see here in the figure. And the microplane model with relaxed kinematic constraint was applied as the constitutive law for concrete. So this microplane model is relatively well known for its capability to predict the tension dominant failure of concrete, even for single crack propagation controlled failure modes. The steel elements, so the gusset plate, the anchor bracket, and also the anchor rods were modeled using 8-node hexahedral elements. And the complete connection is loaded in displacement controlled by incrementally applying the displacement here on the top surface of the gusset plate. As I was already mentioning, we used bonded anchors to form the connection between the connection element and the concrete specimen. And to simulate the bond between the steel anchor rods and the concrete specimen, 2-node bar elements were used. And these bar elements, they were only able or are only able to transfer compression and shear forces. So basically this complete connection comprises the gusset plate, which is this part in the middle, the anchor bracket, which is this L-shaped part, and 8 bonded anchors with a diameter of 16 millimeters. In all simulations, the dimensions of the gusset plate, the anchor bracket, also the anchor spacing, and also the dimensions of the concrete specimen, that means also the distance to the edges, was kept constant. The only thing that was changed was the embedment depth of the anchor itself, which was varied from 80 millimeter to 150 millimeter. And as we can see here, and as I already mentioned before, basically we can describe the complete connection as 2 separate anchor groups, one anchor group here with 4 anchor and one anchor group here with 4 anchors. And therefore, besides the variation of the embedment depths, I also performed simulations where only one of these anchor groups was attached to the concrete specimen. Also, a short note on the material properties. Basically, for the concrete, a C2025 was used. The steel parts were all modeled in as linear elastic, because, as I said, the desired failure mode was concrete Kuhn failure or concrete breakout failure. So the steel parts, they were not expected to go into the nonlinear range. Also here in the figure, you can see the discretization of the bond stress slip relationship for the bar elements. Coming to the numerical results, we can see here in the graph the 3 load displacement curves for the fully attached connection for different embedment depth. And basically the initial behavior is relatively similar regardless of the embedment depth. And we have more or less a linear behavior up to the first peak. And at first peak, we also see the first initial circumferential cracks that occur at the tips of the embedded ends of the anchor. And after we reach the first peak, there is a drop in the load. And while the load is dropping, there are merged the cracks between the anchors start to propagate towards each other. And let's say at the lowest point here, we could see that the cracks have merged basically. And after this drop of load, the complete connection regains some of its strength, while also now the cracks propagate from the most outer anchors towards the concrete surface. What we can basically see here from the load displacement curve is that regardless of the embedment depth, we have a relatively similar behavior in the first loading phase. So up to the first peak and also for the drop of the load. However, the behavior changes in the second phase. So when the connection is regaining its strength. And oops, that was too much, sorry. Yeah, it can be seen that with increasing embedment depth, the behavior in the second phase becomes markedly stiffer. And also in the post-peak behavior, for larger embedment depth, the behavior is more brittle. So at the time where I was writing the paper, or let's say submitting the paper, we didn't perform the experiments yet. In the meantime, we did also the experimental part, so I'm happy to show a little bit of the experimental part here. The experimental program was based basically on the numerical analysis, and as we can see, we used a similar concrete specimen in the experimental part. And here are some crack patterns that we obtained in the experiments, and also the crack patterns on the concrete surface for the numerical simulation. And as you can see, the numerical simulation fits quite well with what we really could observe in the experiments. Also from the shape of the load displacement curve, the numerical results fitted quite well with the experimental one. So also in the experiments, we got the first peak, then a drop in the load, and then the complete connections regained some of its strength up to the ultimate capacity. Also from the value of the ultimate load and the load at the first peak, the results of the experiments and the numerical analysis fitted quite well. But coming back to the numerical results, we also investigated on or compared the fully versus the partly attached connection. And here in the graph, you can also see now the partly attached results with the dashed lines. And we could observe that the load and also the initial stiffness and the second stiffness at ultimate load reduced around 50%. The main difference was really that when there was only when the connection was only partly attached, that there was a rather marked load plateau before the complete failure of the connection arose. So basically, up to the ultimate load, the behavior of the fully attached connection can be more or less assumed as a composition of the two partly attached connections. However, this, let's say, beneficial geometrical effect of the corner, which led to this load plateau, is neutralized by the mutual effect of the two anchor groups when we have the complete connection. So, and based on these results from the numerical analysis, where we could see that we can at least compose the ultimate capacity of such an anchor group by two individual, of the complete connection, that we can compose it of two individual groups, we tried to use the methods provided by Eurocode to come up with an analytical design approach. So basically what we assumed is that the complete connection is treated as two perpendicular anchor groups without any mutual influence. Then the total capacity of the connection is then basically twice the capacity of one of these anchor groups. The ultimate capacity of one of these anchor groups we tried to calculate, or we calculated according to Eurocode 1992-4. And we assumed here two close parallel edges due to the dimensions of the, let's say, columns and beams. We assumed centric loading. That assumption is based on the gusset plate, which more or less distributes the forces evenly to the anchors. And then we assumed the load angle of 45 degrees. So basically the anchor group was simultaneously loaded in shear and in tension. So here we can see the calculated capacities according to Eurocode for one anchor group. So that basically simulates the partly attached connection, and the calculated capacities for the complete connections, let's say. And the first thing that we could see is that the calculated capacities for different embedment depths are essentially the same. So that, of course, is a result of the formulations given in the Eurocode. But what we could also see that compared to the numerical results and the numerical capacities, the formulations given in Eurocode significantly underestimates the actual capacity. So it's very much on the conservative side, and the conservatism of the formulations in Eurocode, or this analytical approach, increases with increasing embedment depth of the anchors. So to put it all in a nutshell, basically the initial behavior of such a fully fastened connection is quite similar for varying embedment depth. There are more differences in the second loading phase when the connection regains its strength, where for larger embedment depths we have a stiffer behavior and also a more brittle post-peak behavior. When the connection is fully attached, the ultimate capacity is around double the capacity of the partly attached connection, and also the stiffness is doubled compared to the partly attached connection. And the applied analytical approach, where we used the methods provided by Eurocode, resulted in capacities which were well below the numerical obtained capacities of the connection. And this conservatism of this approach increased with increasing embedment depth. Yeah, thank you very much. That was all from my side.
Thank you very much, Erik. Very good work. I have a lot of questions, of course, but I would like to ask before to the people if there are some questions from the audience. I cannot see any question at the moment in the web. So I start with one question about the test repetition. So how many tests you did for each case?
You mean the experimental work?
Yeah, experimental work.
Okay, we tested two embedment depths. So one with 80 millimeter embedment depth and one time with 110 10 millimeter embedment depth, and we did 3 tests for each of the embedment
But
depths.
as they ended, how many tests, the numerical identical you could have? Because I would like to understand if you have also in your studies a possibility to compare the reliability of the characteristic or average values in the experimental job. Because I suppose that it could be affected a lot by this, because it's a problem correlated to tension. And so, as we know, usually there is a quite large difference, no? Because you concluded that in the standards, there was a sort of safety because we arrived to 60% of the numerical maximum load, but we have to take into account also the scatter, of course. And so this is something probably that we could use, no? Which is your opinion about it? So
I performed 3 tests, basically 3 similar, 3 tests for one particular thing. Case. Yeah, thank you. And I have to say the scatter was not too big there, actually.
Not too big. That means in the range of which percentage?
I don't have the numbers by heart, but they are well within the limits generally given for testing of anchors.
Okay, so around 15%, I suppose, something like that.
Like the coefficient of variation was less than 15, way less than 50%.
Less than 15.
Yes.
And when you introduce your numbers for the mechanical parameters of the modeling, how you did? So you perform some uniaxial tensile test on your concrete. You use only the model code, or is there some other possible relationship between the compressive strength and the other material? Which was your approach?
So what I showed here in the numerical analysis, that's basically just the normal concrete strength for a C2025 given in the code.
Yeah.
As I was mentioning, it was more or less preliminary analysis for the experiments because I couldn't really tell how big was the load to be expected in the experiments for such a configuration, but I had to plan somehow with it. So I did perform the numerical analysis. For the experiments, I did normal cube tests with 150 millimeter side length to obtain the concrete compressive strength. And from this concrete compressive strength, I back calculated the tensile strength, the concrete material properties.
Yeah, from the model code 2010 or model code 1990, because you know that there is a huge difference between these two situations. And in my opinion, it's better
the formulations given in Eurocode, I think.
In Eurocode, okay.
Yes.
Okay, thank you. Other question from my colleagues?
Yes, please Marco. Yes, thank you. I have a question concerning the real context of this setup. In the real context, we can have previous cracking induced by flexion, for instance, because it is in a beam and column system. And do you think that the previous cracking is able to modify your results?
Okay, that's a good question. So let's have a look at this connection. So basically what happens when the steel bracing is in tension, then the anchors also are loaded. So when the steel bracing is in compression, so maybe we have a buckling restraint brace, let's assume, then the load will be directly transferred from the steel blades to the concrete specimen. Yes, so what happens when the steel bracing is in tension, we have an inward bending of the beams and the columns. So the cracks will close actually. So there will be no cracks or no crack opening when the anchors are loaded.
I'm not sure of that because it is an hyperstatic structure, and the beam could be previously to the tension apparition in the brace. It could be cracked, and these crack, even if they are reclosed, are able to change the crack pattern and the loading capacity of the brace, I think. And it is perhaps in the Eurocode, you have a reduction. What do you think of that? Because
I didn't quite get the point.
Okay, thank you. I have another question.
Please.
How long did you spend to do this modeling, and did you perform the test yourself?
How much time I spent on the modeling? It was quite elaborate, but, several days. It also takes some time to run the calculations. For the experimental part, I think it was around 3 to 4 weeks, which I spent in the lab, and I did it myself with the help of technicians, of course.
Thank you.
Okay, so we are just in time. So I thank you again, Dr.
Yes.
Not yet, Doctor. I hope very soon, Dr. Stehle.